Aloha. In the book of Ecclesiastes, King Solomon wrote, "There is nothing new under the sun." This saying remains strikingly true. The patterns of history often unfold in cycles, and the history of computing is no exception. The early days of computing, 1960s to 1980s. Between the 1960s and 1980s, computing largely required direct programming and text input. At the mainframe level, users had to rely on Job Control Language, JCL, within IBM's time-sharing option to execute commands. For data analysis or computation, languages such as COBOL developed in 1959, Fortran built in 1957, and even assembly language were necessary. These processes were highly technical, debugging was tedious, and the learning curve was steep. When IBM introduced the IBM PC in 1981, its operating system was Microsoft's Disk Operating System, MS-DOS. This environment was purely text-based. Users needed to memorize exact command syntax, and a single misplaced character could trigger a cryptic error message. For many, the system felt as foreign as Martian language. The graphical user interface revolution, 1980s to 1990s. To make computing more accessible, companies began to develop graphical user interfaces. Apple introduced the Lisa in 1983 and the Macintosh in 1984, pioneering the desktop metaphor of icons, windows, and menus. In 1985, Commodore's Amiga featured advanced multimedia and graphics capabilities. These innovations allowed users to drag and drop, point and click, freeing them from the burden of memorizing complex commands. Microsoft soon followed with Windows 1.0 in 1985. Though initially modest in adoption, Windows 3.0, Windows 95, and Windows 98 brought GUIs into mainstream computing. By the 1990s, software applications had become increasingly user-friendly, democratizing access to personal computers. Open source and the return of coding, 1990s to 2000s. Ironically, as graphical user interfaces made computing easier, a counter-trend emerged with the rise of open-source software. In the early and mid-1990s, the R programming language was developed, building upon the statistical language S. Python, created by Guido van Rossum in 1991, gained wide adoption in the 2000s for its power and flexibility. As open-source platforms surged in popularity in the late 1990s and 2000s, many turned to free and extensible tools, such as Python, R, and Julia, introduced in 2012, for data science and machine learning. Today, most academic programs in data science emphasize coding. For many people, data science and machine learning is equated with Python, because this is the primary tool they learned. Yet this raises an important question: is this truly a step forward? If one can build a dynamic dashboard in Tableau or JMP Pro in just 10 minutes, why spend 2 hours writing Python or R code to achieve the same result? The ultimate objective is to extract insights from data. Learning a programming language for analytics can sometimes feel like learning German merely to study physics, an emphasis on the means, rather than the ends. Low code, no code, and prompt engineering, 2010s to 2020s. In response to the complexity of coding, the industry now champions low-code and no-code platforms. These solutions, such as KNIME, Alteryx, and Microsoft Power BI, are often heralded as revolutionary, but in truth, they extend the same pursuit of user-friendliness that GUI began in the 1980s. What is genuinely new today is prompt engineering. Rather than selecting from menus or clicking icons, users can now type natural language instructions into artificial intelligence-driven systems like ChatGPT, Gemini, or Claude. A single prompt can execute complex workflows that previously required manual coding. In this sense, prompt engineering represents a leap beyond the GUI, pushing computing one step closer to intuitive human-machine communication. Local versus remote processing, 1960s to present. Another cyclical pattern in computing lies in the balance between local and remote processing. In the 1960s through the 1980s, most resource-intensive computing took place on IBM mainframes or Digital Equipment Corporation's VAX system, with so-called personal devices functioning merely as dumb terminals connected to central systems. By the 1980s and 1990s, the affordability of Macintosh and IBM-compatible PCs ushered in the era of authentic personal computing, where individuals could process data and run applications locally. Yet this decentralization was short-lived, as the rise of Unix-based and Windows NT servers in the 1990s and early 2000s shifted the paradigm once again toward the client-server model. In this setup, personal computers acted as dumb clients while the servers performed most of the heavy computational tasks. As laptops, tablets, and smartphones became more widespread in the late 2000s, computing was once again decentralized, making one-to-one computing viable for education, business, and personal use. However, the explosion of big data and analytics soon demanded new levels of computational power. This demand was met by the rise of cloud computing. In 2006, Amazon launched its Elastic Compute Cloud, EC2, and Simple Storage Service, S3, a pivotal moment that signaled the start of scalable, on-demand cloud services. Soon after, platforms such as Microsoft Azure and Google Cloud expanded these capabilities, allowing organizations to outsource both storage and computation. Cloud computing went even further than the client-server model, providing scalability, resilience, and flexibility on a global scale. Cyclical, but progressive. From command syntax to GUI, from GUI to open-source coding, from coding to no-code or low-code solutions and prompt engineering, from mainframe to personal computing, to client-server, to one-to-one computing, and then to the cloud. The cycles of computing history are unmistakable. Yet history does not simply repeat itself. We do not regress to where we once were. Prompt engineering is more efficient than the graphical user interface. Cloud computing is more scalable and robust than server-based systems. The cycles bring us back and forth, but each return advances us a step forward. In this way, computing history is not merely circular, it is a spiral of progress. What are your thoughts? Does history truly move in cycles? Share your perspective in the comments below. If you found this video helpful, consider sharing it on your social media. And if you're an instructor, feel free to add it to your teaching resources. Thanks for watching. Mahalo.